All right, I'm very pleased to introduce our, this morning's last speaker, Charles Favre from the École Polytechnique. And he will speak about some new applications of arithmetic geometry to complex dynamics. And his title is Equidistribution of Hyperbolic Centers using Arrow-Kaloff Geometry.
Okay, so thank you very much. So I would like first to thank the organizer for allowing me to give a dynamical talk in front of an arithmetic audience. So I hope that you will find this entertaining. I'd like to first emphasize the fact that there have been a lot of interaction between number theory and dynamics for a long time. So in several directions. So first, dynamical ideas have been used to solve some problems in number theory. So I just mentioned two instances of this. So for instance, the additive number theory, so you have this famous new proof of Furstenberg of the semi-reduced theorem using ergodic theory. Also in this problem of Diophantine approximation problems, that amounts to try to study the approximation of irrational numbers by rationals. So you have the proof of the open-eye conjecture by Margulis of Kinching theorem by Sullivan, which also relied on ergodic theory, and in the context of Kinching theorem on the study of the geodesic flows on the manifold of negative curvature, so on dynamical ideas. And in another direction, so you have a group of people around Joe Silverman, the States, that have tried to look at many of basic conjecture in the study of say torsion points on abelian variety, and translate this or generalize them to a more dynamical context. So concerning rational maps, say on projective variety defined over a number field. So I just put some names here, so Lemmer's conjecture, Manning-Mumford, Mordell-Long, etc., etc. So all these famous conjecture have been generalized to this context. And the original ones came when you look at F being the multiplication by 2, 3, 4, or whatever, on your favorite abelian variety. Okay, so today what I'd like to talk about is in fact an application of Arrow-Kaloff geometry, so theorems about the equidistribution of points of small height, to a dynamical problem, and more precisely to the study of the geometry of the parameter space of dynamical polynomials. So let me begin with the simplest situation, and then later on I'll state our main theorem that we obtained with Thomas Gauthier. Okay, so I'm going to look at a very simple dynamical system. So this dynamical system will be defined on a complex plane. So you fix a complex number, your favorite complex number C, and then you look at the quadratic polynomial Z goes to Z squared plus C. So if you want, this is your dynamical law. And so you're interested in the behavior of the iterates of this map. So you fix now a point Z in the complex plane, and you look at its image under P. And then it's a second iterate, so PC of Z, which I denote by P square of C of Z, and then etc. Okay, so Pn C of Z is the n composite map of PC applied to the point Z. And so in dynamics, when you're interested in looking at what's happening to this sequence of complex points. So basically, two things can happen. So if the norm of Z is large enough in comparison to C, then in these two terms, this is the Z square that will win. And so by iterating this idea, you see that in fact your iterates of your point goes off to infinity. Otherwise, what happens is that if it does not go off to infinity, then the sequence of iterates here remains bounded. So to deal with this, so you introduce this, what is called the filled-in Julia set, that you denote by K of C. So once again, C is fixed. And then you look at the set of points in the complex plane for which the orbit is bounded. Okay? And so you can show that, this is, what I said before, this is a bounded set, but in fact it's also closed, so this is a compact set. And so if you want to study the dynamics of your polynomial, then basically you have to reduce, to look at this action of PC on this compact set, because outside you know that all points are going off to infinity. Okay? And so there is a basic dichotomy here about this, about the topology of this compact set, is that either this compact set is connected, so just one piece, or it's totally disconnected. So either it's a counter set or it's a connected set. And this happens exactly when you have a special point. The special points here is the critical points of your map. So if you look at the derivative of this guy, this is 2 times z. So 2 is over a complex number, so different from 0. So the critical point here is the point 0. And so you have two cases. Either your critical points belong to the field in Julia set, so its orbit is bounded, and then you can show that in fact Kc is connected, or the critical point escapes to infinity, and then in this case you end up with a compact set, a field in Julia set, which is a counter set. Okay? So with this in mind, then this is natural to introduce. So now it's not the set, this Kc lives in the z plane, so now you're looking in the C plane, so basically in the parameter space of quadratic polynomials. And so you look at all quadratic polynomials, so all complex numbers C, for which this field in Julia set Kc is connected. Okay, so once again you can show that this is also a compact set, and this is quite famous. It's called the Mandelbrot set, so which explains this letters M. Okay, so here is a picture of the Mandelbrot set. So here you're in the C plane. Okay. So the point 0, I think, is around here. And then you have here you can see there's some kind of cardioid, and here the tip is 1/4. So here it's a real line, and here it's a point -2. Okay. So what is drawn here is that all these pictures are examples of field in Julia set. So if you pick a point inside this main cardioid, what you can see, so for instance this point, what you can see here is something that is homomorphic to the closed unit disk. So except that the boundary is not as smooth as the unit circle, so it's a fractal set. Okay, and then they took some other, they took some other points. So here, very close to the boundary of the Mandelbrot set, and so you can see that each time where all these field in Julia set are in these 6 examples are connected, and you have some very intricate geometry. Okay, which is basically all these sets are fractal. And then there is a last example, which is here, which is largely outside the Mandelbrot set. And so in this case, the field in Julia set is just a contour dust, so you cannot see anything. This is normal. This is totally disconnected. So it's just to show you a little bit some examples of this field in Julia set and the Mandelbrot set. Okay. So I'll be interested in special points in the Mandelbrot set. So I'll be interested in points, so in the plane of C parameters, for which the critical point is periodic and of period, say, n. Okay. So I recall that this critical point is for z squared plus c is a point 0. And so the critical point being of periodic of period n is just saying that when you iterate n times p of c, you apply this to 0, then you get back to it to yourself. So you get back to 0. Okay, well, if you want exact period, then you have to impose this, but never mind. So let's look at some, so we can actually compute these sets per n. So let's just look a little bit what's happening. So, okay, so per 1, you have to look at z squared plus c. You replace z by 0, and so you get c. So the equation for per 1 is just c equal to 0. So you get 1 point. And then you go on like this. So you look at the second iterate, you apply to 0. So you get c squared plus c, so you can factor out by c. And so per 2 is actually just 1 point, which is c equal minus 1, etc., etc. So for instance, P4, you get this degree 8 polynomials, where you can factorize c squared plus c, which is in fact the equation p squared of 0 equal to 0, okay, times irreducible degree 6 polynomial. And so why you have this kind of factorization is just that if you have a point which is, if the critical point is periodic of period 2, then it's also periodic of period 4, okay? So anyway, so this equation, or you can prove by direct induction that these polynomials here of degree, or have all integral coefficients of degree 2 to the power n minus 1, okay? And so then you can actually, so this is a theorem by Dwady and Hubbard from the 80s, is that actually all roots of these polynomials are simple. Okay, so you can actually compute the number of points in this set per n. So you have this nice formula, and so you use it, so you can check that basically the number of special points in this sense, so of parameter for which the critical point has exact period n is equal to 2 to the power n minus 1. Well, okay, at least it's equivalent to this. Okay, so now the basic question is, so you let this n increase to infinity, so you have more and more points, and you want to describe the distribution of these points. So here is a picture of what's happening. So here it's a picture of the union of all this per n for n in between 1 and 10. And so, so you have approximately 1,000 points. And so what you can see, well, it's not so clear, but so here is the point per 1. So here in green you have the point per 2, etc., etc., etc. And so what you can see is that this point tends to seems to cluster to the boundary of the Mandelbrot set. Okay, and so it is. So it's not so clear because you have a huge region here where you can see absolutely no points. But it is actually a theorem which is due to Levin from the 90s that says that this is true, that this set tends to equidistribute to some measure that is supported on the boundary of the Mandelbrot set. So the precise statement is as follows. So you fix an n, and then you look, so you have 2 to the n minus 1 points, and then you look at the atomic measure that is equidistributed on this set per n, okay? So here's this measure mu n. And then the theorem of Levin says that this converges when n tends to infinity to a measure mu m that is called the harmonic measure of the Mandelbrot set of M. So I'm going to, I'm not going to enter into potential theory here, but suffice it to say that this harmonic measure, the support of this harmonic measure is in fact equal to the whole boundary of the Mandelbrot set. So just one warning is that, so you could try to use this theorem to plot the boundary of the Mandelbrot set, but in fact it's an extremely bad idea because the harmonic measure of a set tends to concentrate a lot of mass to the tips of the boundary. So this is explained a little bit where we see all these points were close to all these tips of the Mandelbrot set, and we don't see any points, I mean up to 10th iterate, in this region where the Mandelbrot set has some kind of channels, if you will. Okay? So from the algorithmic point of view, this is very bad. Okay, so what are the tools to prove such a theorem? Well, you use harmonic analysis. Well, it's normal because here the measure that appears is harmonic measure, so it's kind of natural, if you want. And so basically, to try to prove convergence of measures, it's usually easier to prove the convergence of functions. So here you're over the complex plane, and so you represent a positive measure as a Laplacian. So here the Laplacian is this operator delta, if you want 1 over pi d bar, or ddc, or d square of dx square plus d square over dy square. So it's the standard Laplacian of the complex plane. And so you represent this set of measures, so mu n, and their harmonic measure as the Laplacian of some function. And then you only need to prove that this sequence Gn, which are called the potential of the measure mu n, will converge in a suitable sense, so here's L1 log sense, to the potential of the Mandelbrot set, so to Gm. Okay? So if you want to do this, well, you need to have to understand exactly how this function are constructed. And so in the case of the measure mu m, this comes back, this amounts to this following remark. So first, if you have direct mass at some point, say C, well, what is the potential of this atomic measure? This is just the logarithm of the norm of W minus C. Okay, and so using this, you can check that in fact a potential for the previous measure here, that is equidistribution on per n. Well, you can just look at the nth iterate, well, at the equation defining this set per n. Take the logarithm norm of this guy, divide by the right factor. Okay, so the construction of the potential for the harmonic measure is slightly more involved, but is very much in the same of the same flavor. So first, you need to construct what is called the green function. So you get back. So now you get back to the original framework. That is, you fix the parameter C, and then you look at this limit. So what I said before is that when z is very large, then basically the norm of z squared plus c is essentially a norm of z to z squared. Okay, so you can make this more concrete and prove that, well, so you can look at this sequence of, so you have these normalization factors. So log of the max of 1 and the norm of Pn of C of z. And then this converge uniformly on the complex plane to a continuous function. That is called the green function. So by definition, since I put max of 1 and something, this is a non-negative. And you can, so what's happening is that if the point C is in the Fielding-Julia set, so the orbit is bounded, then this, since you divide by 1 over 2 to the n, this tends to 0. Okay, so you have an inclusion here. So the Fielding-Julia set is inside the locus where this function gc is 0. In fact, you can show the converse also. So it's a way of this function is very important to describe if you want this compact set. And so now, what is this the potential of the harmonic measure of the Mandelbrot set? Well, you look at so you fix your parameter C. You look at the green function of p square of z squared plus c, and then you evaluate this potential at the critical point. Okay. So basically, well, this is equal to this limit here. Okay. So I recall that what you need to show is that, well, Gn converges to Gm. So in fact, these two functions here are very, very similar. So except that for some reason I plug in this max 1 and something. Okay. So at least what is obvious from the definition that this Gn is always less or equal to Gm. And it's also not difficult to show that if you are outside the Mandelbrot set, and then this sequence here, well, the sequence Gn is converging uniformly to Gm. So you only need to look at what's happening inside the Mandelbrot set. And so here is, in fact, the hard work. So there is a trick which uses potential theory, and what you only need to show is that the measure, so Laplacian of Gn, well, if you fix a piece in the interior of the Mandelbrot set, then this mass tends to 0. And then using some analytical trick, then you can show that this implies the previous theorem of this theorem of Levin. Okay. So for the moment there is absolutely no arithmetic, and so there is in fact a nice remark which goes back at least to a paper of Becker and Sia that you can. Well, this sequence of points, this pattern, are defined by polynomial equations with integral coefficient, and so you can hope to well, use more adelic methods to try to prove this theorem of Levin, and so it's actually the case. So what they did is that basically, so you can construct a suitable height function such that this sequence of points per n are all included in a set of points where the height is equal to 0. And then there is a theorem by Autissier which says that if you have a set of points for which the height is small, so here small is 0, then you have some canonical equidistribution theorem. So you can understand the distribution of these points using, say, global methods. So here, this theorem of Autissier in fact goes back to the work of Bilou and Spiro-Mozang, and that was applied to prove the Bogolov conjecture. So what I'm trying to do, what I will try to do now is to explain exactly how to construct this height function, and state this theorem of Autissier and explain you how you get this result of Levin, and then try to compare the two methods. So method which relies basically on the analytical tools, and the method which is more, I wrote adelic proof, that may be more a global method. Okay. Okay. So here is the construction of the height that describe this. That is adapted to our context. So what you need to do is to construct, so what you do is you construct the green function that you did in the Archimedean case, also over the p-adix. So okay, V here is a place over Q, which might be so a p-adic norm or an Archimedean norm. And so now you pick a point in a C of V, so in the completion of the algebraic closure of the of a QP, if you want, if V is a finite place, and then you can do exactly as over the complex. You can also show that this sequence of function converge uniformly to a continuous function that is called the here it would be the V-adic green function, and you can also introduce. Just as before, this potential of GMV, which is the evaluation of this green function at the point 0. So here in this setting, you get something which is very easy. So over the at the infinite place, so you get back this the function that I defined before, and at a finite place, in fact, you don't get anything but this function here. So log plus. Okay, log plus is the maximum of the log and 0 of the p-adic norm of of the p-adic norm of C. So it's very simple. Okay, and so so I can define the height using the standard construction by summing. So assume that, for instance, C is a rational number. Then I sum all this local contribution over at all places. Okay. So the difference between this say dynamical height and the standard height is just that we change the log plus of norm of Z at the Archimedean place by this new function G of M. But it's known that these two functions differs by bounded factor. So in fact, HM differs from standard height by a bounded function. Okay, so it's a Weil height if you want. Okay, so now the remark is that maybe I didn't say this, but if you take a point C which lies in pair n, your critical point is periodic. So at each place, the value of GM of C is equal to 0. Okay, so all these sequences of sets per n are all included in the locus where the height is equal to 0. And so now you can call for this the theorem of Pascal-Autissier, and so which basically says that for this height, if you have any sequence of finite set over Q bar that are Galois invariant, and such that the height is say 0. In fact, you can just assume that the height is tending to 0. And then you have this equidistribution result. And so you get back the theorem of Levin just by applying this theorem to the set to the set Zn equal to per n. Okay? So I should say here that in fact this theorem is basically what you do is you do some harmonic analysis not only in the Archimedean place but at finite places. Okay, and so in a sense, so you remove this later the trick that people used in dynamics by looking at the mass on the interior of the Mandelbrot set by the product formula, and so you gain something by working at all places at the same time. So let me compare a little bit with these two methods. So the analytic method has some advantage in the global method also. So for instance. So we prove with Rivaldo today, we push a little bit this analysis of Pascal-Autissier, and we prove that you can make actually some estimates on the speed of convergence of this measure toward the harmonic measure. So you get some statement like this, and on the other hand, if you use the analytic method, then you can also show that some other sets of interest can describe also the harmonic measure. So here just one example. Okay, so here maybe W is lambda. So you look now at the set of points for which there exists an orbit period n, for which the multiplier is fixed equal to lambda. So you can show also that is a finite set. And if lambda is not algebraic, then it's not defined by an algebraic equation defined over Z. So you cannot use directly the theorem of Autissier. But then still using some delicate analytical tools, then you can show this kind of result. So it's a recent result by Buff and Gauthier. Okay, so now what I'd like to explain you is that in fact you can use the same kind of the generalization of Autissier's result to higher dimension, which is due to Yuan, to get the same kind of results for polynomials of higher degree. Okay, so our result with Thomas Gauthier in fact deals with any degree, but just for sake of simplicity, I will fix the degree to be equal to 3. It is already enough complicated. Okay. So let me look at now the space of cubic polynomials. So up to affine conjugacy, you can normalize in this way. So there are some strange factors. So C and A are complex numbers. PCA of Z is 1/3 Z cubed minus C over 2Z squared plus A cubed. Okay, so why did I choose such a complicated parameterization? It's just that I would like the derivative of this to be particularly simple. So if you look at the derivative of this, I didn't write it down, but what you get is Z squared minus C times Z. And so the critical numbers of, so the ramification locus of PCA is in fact reduced to 0 and C. Okay? So in the sequel I will write C as C1 and 0 as C0. So there are the two critical points of your map. And why I put A cube here just for some reason. Okay, so now I would like to look at some special set in this space of polynomial of cubic polynomials. So there are many kind of special set I could look at. But here I will fix n naught and n1 two periods, so two integers, and I will look at the set of parameters of cubic polynomial for which the first critical point is periodic of period, say, n0, and the second is periodic of period n1. So now it's defined, so your over C2 is defined by two polynomial equations, okay? And so you can show that, so this set now, you can show that this is a finite set. You can actually compute, so I'm going back to this later on. So you can actually compute the cardinality of this set. This tends to infinity when these two periods tend to infinity. And our main theorem can be stated as follows. So it's exactly the same as before. Okay, so except that you're in higher dimension. So here, so we fix two sequences of, say, of periods. So you have n0 k and n1 k, which tend to both to infinity. You assume that they are different. And then you look at the set of parameters of cubic polynomials for which the first critical point is periodic of period n0 k, and the second is periodic of period n1 k. Okay, and then you divide by this so that this measure is actually an atomic measure of mass 1. And then we show that this converge when this thing tends to infinity to some measure, mu m3. Okay, and mu m3 is the analog of the harmonic measure of the Mandelbrot set. And so this is this. So it's called the equilibrium measure of the connected locus of cubic polynomials. So I'm not going too much into the details of what this means because this will lead me too far. But in the sequel, I'll try to explain you how one can use a global method, so this theorem of Yuan, to actually show this kind of result. And along the way, I will define you this measure mu m3. Okay. Okay. So so once again, so I'm going to use basically the same kind of idea. So I'm trying to construct some nice height function that will describe for which all these points in here will have a height 0. And so I'm going to define as before. So first, so I fix C and A. So I fix a cubic polynomial. So I can look at this green function. Okay, so now I have to divide by 1/3 to the n. 3 is the degree of your polynomial. So you can also show that this converges uniformly on the complex plane. Okay, and then I can look at two functions now. So because I have two critical points, I can look at, say, G naught, which is the evaluation of this green function on C naught, and G1, the evaluation of the green function on the next critical, on the other critical point on C1. Okay, so this is a two function, and the connected locus, so you're in the space of cubic polynomials. So the connected locus, this is a set of points CA for which this K of this Philly-July set is connected. And you can actually show that this is exactly the set of parameters for which the two critical points have bounded orbits. Okay, so it's exactly saying that this connected locus is, so if you want, this is the generalization of the Mandelbrot set, except that, so I would like to show you some picture of this, but it's kind of hard to picture something dimension 4. So the connected locus, at least, it's also, well, the locus where these two functions, G0 and G1, is are equal to 0. Okay, and this is harder than in the quadratic case, but you can show that this is, so the fact that this is closed, so it's just this equality here, is also bounded, so it's a compact set. Okay, and so what is the equilibrium measure? Well, okay, so now what you do is that, so you have these two functions, G0 and G1, you take the max of the two, why not? And then you take, so this is this function capital G, okay? Which tends to, it's equal to, so in fact the connected locus is precisely the locus where capital G is equal to 0. And then you're looking not at the Laplacian, because when you're looking at when you look at the DDC of G, this is not a measure; it's something which is of higher dimension. So you look at the corresponding operator in dimension 2, which is called the Monge-Ampère operator, so which is denoted usually by DDC to the square. So I'm not going to define this precisely. And this measure is actually the Monge-Ampère of this function G. Okay, so you're not supposed, I will not comment more on the definition of this, so this is purely analytic, but at least this gives you a way to handle this measure mu m. And so just as in dimension 1, well, you can try to copy the analytic proof and show that, okay, so I didn't write here, but you also have the, so you can also understand this measures equidistribution on the set per n naught n1 in terms of some functions, and then if you can use this to try to prove that this function converges to G to actually prove the previous theorem that I stated. And so the warning here is that in fact the analytic method are not strong enough to prove the theorem that I stated. So, okay, so this in this theorem here, I don't have any assumption beside the fact that the two periods are going off to infinity. If you just want to work at the Ackermann place, for the moment we only can prove this, but if one period goes to infinity much faster than the other one, in a non-infective way, okay? So if you want the theorem that I state here, for the moment we don't know any other method that relying on this on global methods. Okay, so the strategy is well, you just copy what I explained for quadratic polynomials. So you construct a natural height for which you check that this sequence of points are in the locus where the height is equal to 0. Then you apply Yuan theorem, which is on the equidistribution of point of small heights, which is the generalization to higher dimension of the former theorem of Otissier that I mentioned before. Okay, except that there are a couple of difficulties. So, so the first difficulty is that, you will see later on how to define this height. But the height for which you can apply Yuan theorem are very special. So I'm going to state the theorem of Yuan in a few slides. So the height is defined starting from some metrization of ample line bundle. And so if you want to apply this result, well, you need to identify the right line bundle and to identify the right metric to put on it, and to check a couple of technical assumption, that is that the metric that you put on this line bundle is this, horrible terminology, semi-positive adelic metric. So I'll come back to that later. And also there is a second point that does not appear in dimension 1, that you need to check that your set pair n0 and n1 does not by mistake cluster on some curve in A2. So it means that you need to check that the points should be generic. And so in fact this is the hardest part of our work, and so it's something that is very delicate. Okay. So here is the construction of the height. So basically, I'm just copying the construction of the height that I had before for quadratic polynomials, except that it's a bit more involved. You replaced 2 by 3 and so on. So so here the height will be defined by a sum of local quantities. So a sum of some local heights. So it's a sum over all places of Q. And so the local heights are defined starting from the green function of your cubic polynomials, except that here, so V is no longer Archimedean, could be a p-adic norm. And so GV is the corresponding function in the p-adic world also. So you look at the max of the evaluation of this green function at the 2 critical points. Okay? And so for quadratic polynomials, what I said is that this for all primes p, in fact, what you got before is just log plus of norm of c, so it's something which is very simple. Here it's also the case, but only for prime p that are larger or equal to 5. For p equal 2 and 3, well, the situation is much more complicated. So what's happening is that you, starting from the definition of the standard height, well, you're doing something special at the Archimedean place and also at the 2 places 2 and 3. Okay? But never mind, well, this height function is a perfect Weil height, and it differs from the standard height by just a bounded factor. And well, once again, so if you take a point in here, it means that the 2 critical points have bounded orbits, or they are periodic. So well, this quantity here is 0, this one is 0, and for each places, so when you sum 0 quantities, well, you get the 0. So this just means that this set is included in the locus where the height is equal to 0. Okay. Okay, so and then you can apply this theorem, and then this is the end. So okay, so it's so here is a result of UN. So the situation is as follows. So it's just to explain that you need some time to try to translate this theorem to your actual situation in the dynamical context. Okay, so UN theorem says the following. So you pick X to be a smooth connected variety defined over Q. In fact, it's defined over any number field. And D is just a dimension of X. And you pick some ample line bundle. And you have a data which is the following. So for each place, finite and Archimedean, you put some metrization of this on this line bundle, and you need some technical assumption. So you need this metrization to be continuous. You also need this metrization to be semi-positive, so at least at the complex plane, a complex place. This means that when you look at the curvature of your metric, this is something that is positive. So the best case would be that the curvature would be, this metrization would be smooth, and positive means that the curvature is just a Keller form. But here you really need to go to more singular metrization, and so semi-positive is something which is more delicate to define, just that the curvature is a positive closed one-one current, something like this. Okay, and so so once you have such data, so it's so this is something which is basic in algebraic geometry. So you can construct a natural height. So on the q-bar point of X. Okay, so it's maybe not R plus, a priori it's just with value in R. And the statement is as follows. So now you take a sequence of finite subset of q-bar points in X that are invariant or the action of the absolute Gala group. And you assume that the height of on this finite set tends to some value, which is, say, the generic value of the height on X. So it's this quantity. And then you assume also something else. You assume that your sequence of finite set does not cluster too much on a fixed subvariety, in the sense that for any proper subvariety Z inside X, you want that the proportion of points that of Fn that falls into Z is very small in comparison to the total amount of points. Okay, so this is this statement. Then you have this convergence. So okay, so let me translate all this in our context. Okay, so this X is in here for us will be just P2, so it's very simple. The ample line bundle is O of 1, so it's just fine. And then the metrization is the metrization that comes from all this function G of V. Okay, so when you have a function G of V, then you can define a natural metrization on O1, at least on A2. And then, so one of the first things that you have to do is that you have to check that this metrization is semi-positive continuous adelic metrization of O of 1. So it's not so complicated, but you need to look at this. And then when you look at the definition, the associated height function attached to the metrization is precisely the one I defined before, this h of M3. Okay, and so you're in a very good position to apply Yuan theorem, which tells you this. Well, assume that you have a finite sequence of a sequence, sorry, a finite subset of okay, x here is P2, say of points in Q bar the square that are defined over Q, for which the height is equal to 0, or tends to 0, and such that you have this genericity property that it does not cluster too much on any strict subvariety of P2, and once again X is P2. Then you have this equidistribution result at the complex place. So if you look at the measure that is the probability measure that is equidistribution on this set Fn, well, this converges to this measure mu M3. Okay, so yeah, okay, so yeah, nothing has changed except this red red thing is that basically everything is I should not say easy, but it's a quite direct check to make, except that if we want to prove our theorem, we need to check this assumptions. So remind that this I will take Fn to be this sequence of points for which the two critical orbits are finite, or two critical points are periodic, and so I need to check that if I pick any curve inside C2, where the number of points of such points is very small in the number in comparison to total number of points in of per n not n1. And so this is in fact the core of analysis. So this is something that is very difficult. And so so the statement is as follows. So I recall so what were our situation. So we had these two, so n0 and n1 were the period of the two critical points that I was looking at. And I was asking that these two periods were different and that they both go off to infinity. Okay? And then I pick any curve in A2, and then I'm looking at the set of my special points here that falls into this curve, and I divide, I look at the proportion of such points corresponding to total number of points here. And the claim is that this is equal to 0. Okay, so this means that I can apply Yuan theorem directly, and then I get our stated result. So the proof of this is at least at a formal level, not so complicated. What you do is that, well, you apply Bézout theorem. So this set per n0 n1, okay, here is defined as intersection of two curves that are defined by polynomial equation. Okay, so this is defined the intersection of what you look is a PNCA of C0 equal to C0, and the same for C1. And you can compute the degree of these two curves, then where this is 3 to the power, the length of the orbit that you're looking at. Okay, so you can expect at least that this total number of points here is equal by Bézout is equal to 3 to the power, the sum of these two periods. And also, well, if you fix an irreducible curve Z, well, you can look at this inclusion here. And so it's not difficult to check that once again by Bézout theorem, now the number of points that fall into a curve Z is bounded by maybe twice the degree of Z times 3 to the power the maximum of these two periods. So if you divide the 3 to the maximum of the two periods by 3 of the sum of two periods, and if the two periods goes off to infinity, then you get something that goes down to 0. Okay? So so it's a fact that you can actually make this work, that you can apply Bézout theorem directly, but it relies on the following theorem, which is the generalization of a theorem of Doedy and Hubbard to a higher dimension, and goes which is due to Adam Epstein, and which says that if you look at these two equations defining your set of special points, so these two curves, so that might be reducible, they might be singular in general, but when they cross, they are smooth and they cross transversely. Okay, so this transversality result. So these two curves that define your set here, so the intersection of these two things. Okay, they are smooth at any of the intersection points, and they intersect transversely there. So once you have this, well, you can apply directly Bézout theorem, and then you're done. And so, I would like to make one comment on this, is that in fact, to prove this result, to use the Teichmüller theory. So it's not the Teichmüller lift as before, but so you really use the Teichmüller theory, and this in here you really use purely complex analytic methods. So although the theorem here, the theorem, so these two curves are defined over the rational. So this statement and the computation here is purely an algebraic problem. Here it really relies on some complex, looking at the contraction properties of some operators in a nice complex binary algebra and so on. And so for the moment we don't know how to do that without using this Teichmüller theory. Okay, so to sum up, to prove our main theorem, what we did is that we look at all places at the same time, and we did some harmonic analysis at each place, and to apply the result of UN, then we had to estimate some quantity of number of some algebraic set, and we realized once again on an analysis which is purely at the Archimedean place. So there is some kind of interaction with global and analytic methods to prove our main theorem. So I'm not sure exactly how much time I have left. Okay, so now I'd just like to comment a little bit on what one can do beyond this result. So what I was looking at special points. I mean, point for is the true critical points are periodic. And I said that these points were, in fact, the points for which the canonical height here, HM3, were equal to 0. But you can also look at more general points, just at the point for which this canonical height is equal to 0. And in fact, using Northcott theorem, so it was proved, it was an observation by Patrick Ingram that, okay, so this special point here are precisely the point for which the critical points maybe are not exactly periodic, but have finite orbit. So what is said, they are pre-periodic. So they can go off for some terminal arbitrates, and then they fall onto some periodic orbit. Okay, so these special points here are exactly the one for which both critical points have finite orbit. And so, well, you can ask the question now: is it possible so you pick a curve inside A2? So A2 is the space of cubic polynomials. And you assume, well, you have an infinite number of special points in here, and is it possible to describe the geometry of this curve in dynamical terms? So basically, this question amounts to, so it's connected to the Bogomolov conjecture. So here, it's maybe the analog of the, it would. I mean, I didn't state any conjecture here for the moment, but. If you ask this kind of question for a standard height, this corresponds to the Bogomolov conjecture on this semi-abelian variety. Okay. And so here is a precise, so there is a recent work by Becker and DeMarco where they stated a precise conjecture on this problem. So it's kind of complicated. Okay, so I'll try to explain this informally, and then I give some examples. So what they say is that this is a precise conjecture saying, okay, well, pick a curve inside the space of cubic polynomials and assume that you can find infinitely many points in V, such that both critical points have finite orbits. So in other sense, you can find infinitely many points for which this dynamically defined height is equal to 0. Okay? Then something special is happening. Okay? So something special means what? Well, what could happen that in fact one of the critical points has a finite orbit for all points inside V. Okay? So it can happen for one of the two critical points. Or there is some more interesting behavior that can happen. What could happen is that, in fact, the orbit of the two critical points collides. So, but this happening for all v inside the curve. So, what can happen is that, in fact, well, I don't know. So, for the two correct points are C and 0. Maybe C is mapped after 1 or 2 iterates onto 0 for all points inside v. Okay, then you can in fact show that in this case, this set of special points are Zariski dense inside V. Okay, so well, this is slightly more complicated. Okay, so let me give maybe two examples of kind of special curves that can happen in this conjecture. So here I just so I remind that C and 0 were the two critical points of my cubic polynomial. So what I can look at, for instance, is that the curve for which the first critical, or the critical point C is mapped after one iterate to the other, okay? And then, so this defines this curve. In fact, you can compute, so it's a union of three lines. And on these 3 lines, when the set of points for which the height is equal to 0 is Zariski dense on each of these 3 lines. Okay, so you have also more complicated examples. So here I look at this family. So T is, say, a complex parameter. Okay, so it's not exactly the same parameterization as before, but by conjugation, by deletion, you can come back to the previous family. So this in the space of cubic polynomials, this defined an irreducible curve parameterized by C. So here, the two critical points are 0 and 2t. You can just compute the derivative of this function. And what's happening is not that 0 or 2t are mapped to the other after a finite sequence of iterates, but that there is a symmetry of this family. So ft here is pt. So there is a symmetry here, which is minus z plus 2t. It's an involution that commutes with your polynomials. And so your 2 points are somehow related by this symmetry. Okay, so the symmetry is permitting these two critical points. And so you can check also that in this family, well, the set of special points is also Zariski dense. Okay, so well, what is written here is a way to include this kind of example. So the example of some kind of symmetries between that exist for all parameters inside your curve. Okay, and let me just finish by, so the conjecture is still open as far as I know, but they have some partial results. So Becker and DeMarco, they have some partial results, and for instance, they prove, okay, so the following. So you look at the space of cubic polynomials, and then you look at this curve. So you fix lambda, and you look at the set of parameters for which you have a fixed point with a multiplier lambda. Okay, so this is a 1-parameter family of curves that covers, if you want, C2. And then you can they prove the conjecture for this family of curves. Okay, so they show that, well, per lambda contains infinitely many special points, so this point of height 0, if and only if lambda is equal to 0. And lambda equal to 0 means that one of the critical points is actually fixed. Okay, so I think I'll stop here. Thank you.
Okay, thank you for a very clear lecture. Does anybody have any questions? Yes?
Is there a reason for which? Okay, thank you. Is there a reason for which these families of cubic polynomial is particularly interesting?
Hard to answer. Okay, so I should answer in this way. In complex dynamics, this is fundamental not only to pick one polynomial and look at the dynamics of this polynomial, but also understand how the dynamics changes when you're moving the parameter. Okay, so you have a huge amount of literature on what's happening when you look at a quadratic polynomial, and then this family is one-dimensional. And then recently, people introduced techniques to go beyond this, because I like very much quadratic polynomials, but in general, you're interested in polynomials of any degree, not just 3, 4, 5, anything, okay? And so then you have to deal with, you have to introduce some Well, some techniques that are more adapted to a higher dimensional moduli space, if you want. So I'm not really answering your question. I'm just saying that this, from the dynamical point of view, you never ask this kind of thing. It's just completely natural somehow.
All right, any other questions? Okay, well, please join me in thanking Charles again.